Right, guys. I saw your presentation last time when we met, and I just want to emphasize a few points on your processes and to actually make you understand a process data, right? What we agreed on that day was that we need to know processes, right? We need to know processes, what the process is, process scheduling, operations on processes, then the fact that if we have got one or more processes that are running at the same time, they may need to communicate. Look, there are two types of processes. Independent processes that are running concurrently do not need to communicate. But cooperating processes, when they are running concurrently, they need to actually communicate, right? So these are the processes that we mainly talk about when we are talking about inter-process communication. We are talking about cooperating processes and how they actually communicate. But if two processes are running and they are independent, you don't need to worry about them. So these are the concepts that you need to know, guys, about process, or the concept of a process, to say what is a process, what's the difference between a process and a program, what is process scheduling, and what happens during process scheduling, and so on and so forth. These are some of the things that you really need to know. Although you explained them well during the presentation, but I thought I was going to make some additions, further explanations, making you prepare for the examination, right? So these are the objectives of our presentation. Let me not worry about them. Let me go to the process concept, of course. Yes. So we say a process is a program in execution. Think of your word processor. When we install a word processor, we are installing it on the hard disk, right? Before we start it on, it is just a program which is lying idle on that disk. But when we start it, it is going to be taken into the main memory and part of the running part of the word processor into the RAM, into the processor and the main memory. So when a process comes into the processor and the main memory, it's now an active, the active version of a program. The active version of a word processor is what we call a process, right? So we can say a process is the program from the context of the operating system, because now it's now running. So a program in execution is what we call a processor, or we can say process that is progressing, that has been started, right? That's a program that has been started is a process. So when we are talking like this, to talk about a single process, assume that there are no parallel execution of instructions. Maybe the process is sequential. It's executing one statement, one program statement after another, right? So when a process is running in the memory of a computer, look at what we have in the memory of a computer. We have some program code, also known as the text section. We also have the current activity, that is the current, the program counter, which is pointing on the current activity that must run, or the next one. Then we have a stack, a memory stack, where function parameters, return addresses, local values are stored. Then we have the data section, which contains global variables that can be accessed by any part of the program. Then we have a heap, which is dynamically allocated during runtime. So these are just the components of memory, right? So we have said a program is a passive entity. It is on the hard disk and it has been installed, but it's not yet running. So the active version, when we start a program, when we click a program so that it can start running, it becomes a process. So program becomes a process when execution starts and it's loaded into the memory and possibly into the processor. Execution of a program can be seen through the graphical user interface, where possible, where the program is a graphical user interface, or we may write some commands if it is running on the command prompt, something like that. So, but remember, we have said we can think of a program as a process, assuming that it's running sequentially and there is exactly one instruction that is being executed at each point in time. But does that happen to all programs? No. Some other programs will have several processes running at the same time, right? Or a computer can have several processes running at the same time. That's a real world scenario. Imagine you are having your computer, your laptop, you are typing your assignment, at the same time you are listening to music, right? At the same time your WhatsApp is on behind. These are real programs that we use nowadays. Our computer does no longer wait for a single instruction to run at a time. Instead, it will be having parallel instructions, running the WhatsApp instructions, receiving messages from WhatsApp, playing music for you, at the same time typing. You are typing into the word processor. So it actually means your computer is running many processes, or it is running many applications, or active versions of the same program have been activated, right? So look, this is generally the process in memory. We have not yet gone to the actual processor. So the memory is divided into the stack, then the main working area there, then the heap, then the data, then the text, the data, then the text. So look at what it looks like. So the process states, you have to know them. A process will always have these 5 states. New, when you click a process and it has not yet started running, we call it a new process, right? Maybe it's now in the ready queue, but it has not yet started running. Then we have a running process. It means the process that has grabbed the processor, that is actually in the processor, running. Then waiting, a process is waiting for some event or for some input, or an interrupt has made it go to the wait position, something like that. Then ready, which is in the queue, ready to be assigned to the processor. Then terminated, a process that has carried out all its activities and it has reached the end. So look at the 5-state process, guys. I want you to know that diagram. Look at the new version of the process there. When it is admitted into the queue, it's now ready. Then when the scheduler dispatches it into the processor, it's now running. During the process of running, it may wait. It may wait for an input or output event, or it may receive an interrupt. So look at what happens. If the input or output event completes, it gets back into the ready queue to take. When it is dispatched again, it gets running until it has completed its stages. Then it gets into the exit point where it is terminated. So this is the 5-state process, guys. I want you to know it, to explain every stage, and to be able to draw this diagram. Then we talk of the process control block, right? The process control block is the accounting system of the whole process that is taking place, right? So look at what is happening. The process control block, look at the version of the process control block there, look at the stages there. Process, the items that will be in the process control block. Look, the process state, the process number, the program counter, then all the registers, or the variables, or the storage locations, then the memory limits, then the list of files. Then look, this blue section here indicates that we have simply talked about a few items of the process control block, but otherwise we don't only have files, we may have printers, we may have network issues, and all those things that are related to a process. They need to all be recorded within the process control block. So CPU registers simply means where items are being stored. So CPU scheduling information, this is the priority value of a program. Remember, even a program is running and it's already in the processor, it has already been dispatched into the processor. It still has to keep its process state, because Remember, when we are talking about scheduling algorithm, we shall see that some scheduling algorithms will preempt the process if another process with a higher priority value comes in. So it actually means during the moment the process will be running, it still keeps its priority value. And it compares its priority value with the other processes that are within the queue. Then we have memory management system, memory management information, the memory that has been allocated, how big it is there still need for more memory, or the memory is sufficient, and so on and so forth. Then accounting information, how much of the CPU has been used by a process, and at what stage does the process need more power or more resources in the next few moments, or it's now releasing some of the resources, and so on and so forth. Accounting info, that's accounting information. Then input output status information. What are the inputs required? Are they coming from the keyboard? What are the outputs? Are there some printers? Is the information coming from the network, or is being logged in from the environment? We really don't know the kind of process, but just the process control block should have as much information about the current running process as possible, right? So far, we have been assuming that a process is a single application, and that single application does not have sub-processes within it. But the reality is, every process, like a word processor, can have many processes that are running at one time. Remember, for example, when you are typing into a word processor, you are typing on an empty page. Maybe you have copied some other items that are on the clipboard, and there is a special spell checker behind, which is checking every word that you are typing. So the process of creating a document is one other process. The process of checking spellings and grammar and syntax is another process that is running in the background. This is why when you type wrong information, or when your information is ungrammatical, you will see that there will be red squiggly lines. It actually means the word processor is marking and validating what you are typing in. So in a real world, we have every process will generate sub-processes, and the sub-processes within the process will run concurrently. It actually means when we start a single application, we will have several processes that are related to that same application, and they are running at the same time. This is what we mean by threads. So when we have threads, it actually means the process is becoming more complex. Each process now has its own process control. Each sub-process or thread now has its own process control block. Right? So this is a representation of a process in Linux. Don't worry about it. Then we talk about, if we are saying, we have said a process can have threads, to mean that it is a single process that has generated multiple sub-processes within it. But at times we may have many processes running within the same computer. As one process is running, others are queued. So that aspect of the computer which manages the queue is called a process scheduler, which selects among the available processes in the queue, and it judges to say which one is the next process to run. Why do we want a computer to be able to manage many processes at the same time? This will maximize utilization of a computer to make a computer more efficient. Assume that there are many processes or there are many applications that are running at the same, that are in the queue, but the computer has one core or has exactly one processor. It means for us to maximize its use, we are always emptying processes that are not on high demand and replacing them with processes that are on high demand. So we are utilizing our single processor by interleaving processes. If we see that process A needs resources, we stop it, shelve it somewhere. Then we let process B, which already has resources, come in and run. So the goal here is to assume that we've got a single processor. If we have a single processor, we can also have many processes that are waiting in the queue, and each time the processor is running a single process. And when this process being run needs to rest or wait, we need to make another process get into the processor and start running. So it actually means we will be having a ready queue with many processes waiting for the scheduler to dispatch it into the process, into the processor. So it actually means processes can migrate among queues if there are many processes, and now queuing becomes complex. Look at what we are saying. We have a ready queue, a queue for the processes that are already ready to be run. Then we have a wait queue, a queue of processes that are waiting for resources or some events. Right? Then look at what happens now. We now have a complex queue where we have a single CPU there. Look, we have a single CPU there, but we've got 1, 2, 3, 4 queues, right? The first queue waiting for input and output. The second queue waiting for a time slice. The third queue waiting for child processes to finish. Fourth queue is a queue of processes that have been interrupted. So this is now our ready queue there. You see. So this is a representation of a single processor that has many queues that are waiting to be run by it. So look, we have an example of two processes that are running, process 0 and process 1. So look at this point. Process 0 is executing. Now it receives an interrupt. Then its process control block begins serving. It serves the state or the context of it. Then we load the process control block of process 1 into the memory and into the processor. So you see, as process 0 is executing, process 1 is idle. When process 1 becomes idle, when process 0 becomes idle, process 1 is now executing. When process 1 stops executing, process 1 starts executing. This is exactly what is happening. So it actually means we have a single processor that is running a single process at a time. So what do we mean by context switch? Context switch means we are saving the whole process that is currently running. We shelve it. Then we take the saved state of an old process, we place it into the main memory and the RAM, and then it begins running. So the context simply means the state of the process control block at any point in time. That's what we mean by context. So switching context means saving the context of the previously running program and loading in the context of the process that has been waiting in the queue. So remember, when a context is changing, there is some overhead that takes place. It means the process itself and memory and registers, they are doing some work. This is what we mean by overhead. So the operating system is encountering some tasks that also need resources. So the amount of time spent during context switch depends on the kind of processor and register. How complex is our processor and the registers? All those things determine what is going to happen during the process of context switch. Here we are simply trying to show you that multitasking can also happen in mobile systems like Android. No matter how small a phone might look, but the modern phones nowadays are able to run multiple processes just like a computer. So operations on on a process. A process is started. Once a process is started, it is then dispatched from the ready queue into the processor, and it also have to be in the memory. So process creation is starting the process. Process termination is the ending. When a process is created, it may create other sub-processes or child processes or threads, which in turn create other processes to form a tree of processes if a program is complex. Generally, processes identified and managed via a process identifier. It means each and every process that is running has a process ID which identifies it. Even a thread, when it is running, it should have a thread ID. Then we come to the sharing of resources. If a process is complex and this has created threads that are running concurrently, it actually means resources between or among the sub-processes need to be shared. Children can share a subset of parent resources, or a parent and child may share resources, and so on and so forth. On execution, we can have a situation where the parent process and the child process are executing at the same time, or we can have a situation where the parent process waits for the child processes to execute, then it receives the results and then begin executing. Right? So look at the process creation. We need to identify the address space. We need to load the child program, and so on and so forth. This is a case study below there where we are indicating how a process is created in Linux through the fork and execute functions. So look at a tree of processes. It actually means this is the mother process, which has created 1, 2, 3 processes, and process 1 has created this one, and this one has created this one and that one. You see what is happening? So we are saying this process which started which has PID 1 now has grandchildren of processes and so on and so forth, as a tree of processes being generated by the same process. So let's not worry about the code there. Let's not worry about the code. Then we talk about a process termination. This is where we are saying once a process has been started and all its steps have been carried out, it will get to a point where it needs to be terminated. So some operating system allow the child to exist if the parent, they do not allow the child process to exist if the parent is terminated. In some, the child can actually exist independently of the parent. This is where we talk of cascading information. All children or grandchildren, etc., will share the same information. Therefore, if the parent is to be terminated, the parent begins by terminating child process and grandchildren processes before it terminates itself. Some parents may wait for the termination of the child process by using the wait system call and so on and so forth. So systems operate differently depending on the way they were programmed. So we are talking, this is just an example of how Android works. Then an example there of Chrome browser and how it works with many tabs. Look, each tab is a thread or a sub-process. Then that fact to say we can have many processes running, or we can have many threads or sub-processes running within the same process, makes it necessary for us to talk about inter-process communication. So processes can be independent or cooperating. Cooperating processes can affect or be affected by other processes, including sharing of information. Reasons for cooperating of the processes may be sharing information, computation speed up, modularity, convenience, etc. There are so many reasons where we must make process dependent on each other. So cooperating processes as opposed to independent processes, they need inter-process communication. And inter-process communication can happen through shared memory, message passing, right? And remote procedure calls, they are not written here, right? So look, this is a diagram where a shared memory, there's a shared memory between process A and B, and they are sharing the memory. And look, B there, this is an example of message passing, right? So the producer-consumer problem, don't worry about that one. Let us talk about inter-process communication through shared memory, right? It means two processes that are running concurrently will create a memory space where they can share. Each one can read and write from that. The communication is under the control of the user processes, not the operating system. Now the challenge that comes to exist is that processes, when they are using the same memory location which they are sharing, it means they need synchronization to promote orderly of reading and writing so that information does not get dirty. So synchronization is not being discussed here, but just understand that synchronization is promoting the order in which each among the running processes, they should have the order in which they write and read from the same shared memory. Don't worry about the code, don't worry about the code there. Buffer simply means shared memory locations, right? So this is where a way of sharing in which we are writing information into the same memory location. Don't worry about code or this code, right? Of course, we shall talk about rest conditions. Rest conditions. The rest condition simply means when we have a running process, two running processes, which want to access the same resources or the same memory location together, then that's rest conditions. Processes are competing to access a memory location. Another way of sharing data or resources is through inter-process communication. Here there is no shared memory between or among computers, but what is happening is they are sending messages between or among each other. If processes P and Q wish to communicate, they need to establish a communication link between them, and then they exchange message via send and receive. Implementation issues, how links are created, we shall talk about it in detail. So the link might be physical, you know, a physical network. The link might be logical, right? But as long as communication is taking place, it actually means this is inter-process communication. The communication might be direct or it might be indirect. That also doesn't matter as long as communication is taking place. So you need to understand direct and indirect communication. I'm scared that my file might be too large there. So please try to understand. Then the concept of synchronization, it actually means that we need our processes to run in an orderly way if they are sharing information so that information doesn't get corrupted. If there is no synchronization, information is likely to be corrupted or to face some challenges. So don't worry about this code. Buffering simply means storing information Now we have examples of inter-process communications there. We don't need to worry about those examples. All we want you to know are the basics of inter-process communication. Of course, you must understand about sockets and how they work. Look at this is socket communication. I will not explain into detail. You shall read all that. Look, we don't worry about all this code. Then we want to understand that a remote procedure call is a call that is being made by another machine, and a function is going to execute on another computer that is on the network. So this is how a remote procedure call is executed. You can follow these steps.